Okay, this is 1.2 horizontal and vertical shifts. So this video is made for an introductory calculus class, and horizontal shifts for us we're going to represent using H, and vertical shifts we're going to represent using K. This follows a video learning about the library of functions of some basic functions that we're going to play around with transformations on. The objective is, given an equation or graph, identify or apply the horizontal and vertical transformations. First, we're going to talk about vertical shifts, which we identify using K as the variable that we use to describe the value that we're either adding or subtracting to the end of the original expression. For example, we have y is equal to the absolute value of x, and then we add a 2 to the outside of that function. So you would recognize this first one to be an absolute value function, and the k value here is going to be equal to 2. It's going to move our original graph up by 2 units. Y is equal to the square root of x minus 5. In this next example, k is going to be equal to 5, and we're going to move, that means it takes the original graph of square root of x, and it's going to move that graph down by 5 units. Each individual point will move down by 5 units. In this next example, x to the third, you want to picture the basic function of x to the third, but we have x to the third minus 1/2. So in this case, k is equal to 1/2. And you would move the entire original function down by 1/2 unit. And notice that it's a constant that's either being added or subtracted to the original function. Another example that might look a little trickier would be if you had y is equal to 6 minus x squared. In this case, you would say k is equal to 6. It would move the graph of negative x squared up by 6 units. So a generalization that we can make is that if given this form, we're taking a look at adding k to the end of the function, right? We're adding a constant to the function in general. You can say if k is positive, and the way that we say that in class is k greater than 0, if k is positive, the graph is going to have a vertical shift up. If the k value is negative or less than 0, the graph will shift down. Horizontal shifts are a little bit trickier, and we use the variable h, a lowercase h, to represent a unit of a horizontal shift. Notice the placement of h relative to the original function is actually happening on the inside and affecting our input values of the original function. I also want you to notice that the standard for a lot of textbooks is that we're going to subtract that value. So it's a little bit trickier to identify, but I think when you see the results of the graphs, it might make sense as to why they do that. So let's go through a couple of examples. The first one is y is equal to the absolute value of x minus 2. Notice the minus 2 is on the inside of the function. So that's how I know it's not a k, if it's acting on the inside of the parent function. So I know the parent function of this one would be absolute value. Would be the parent function. But this h value, we're going to say h is equal to 2, because notice the original form I have, that I pointed with an arrow up there, it's x minus h. So h is actually, we're going to record it as positive 2, and it's going to shift our graph to the right by 2 units. The next one, y is equal to x plus 5 quantity to the third power. Again, that 5 is acting on the x, so it's happening on the inside. It's affecting the input values before it goes through the function. So the parent function of this one would be the cubic function. So we'd take that cubic function, and we're going to say the h value in this case is negative 5. So it's going to shift the entire graph to the left by 5 units. Y is equal to the square root of x minus 7. Again, we're not subtracting a 7 from the outside of the radical. We're subtracting it from the inside of the radical. So this graph would look like the square root function. It would look like that hook. But instead of starting at 0, let's see where it goes. H in this case, again, we have subtraction, so we're going to record this as positive 7. And that means that this entire graph would shift to the right by 7 units. Let's do a few examples that show going from the graph to writing out what the equation will be. So we're going to do that by identifying the parent function, hk, and describe any shifts that happen. And this will help us write out what the equation will be. So the first graph I notice, it looks like that V shape. So this is going to be a parent function of absolute value. I also notice that what used to be at the vertex of 0, 0 has now moved down 2 units to 0, negative 2. And it also looks like the rest of the points have the same relationship to the vertex. So we move up 1 and over, so that hasn't changed. So I can say that this is an absolute value graph that has a vertical shift down 2 units. We can say in this case, k is equal to negative 2. So then our new function is going to be y is equal to the absolute value of x minus 2. This was a vertical shift down. By 2 units. The next function, I noticed that hook shape. It's really distinct because you have a moment where it's not continuing in the other direction. I noticed that it's oriented in the same way as the original graph. This is the square root function. So I'm going to use that to create the equation. In this case, I noticed that there was a shift to the left from the original graph by 2 units. So that means that our h value is going to be equal to negative 2. However, be careful when you go to rewrite what the equation should look like. Keep in mind a couple things. One, that h is going to go on the inside of the function. So when I create my square root, I'm going to do x but leave room. This is going to become the square root of x minus a negative 2. So this is really the square root of x plus 2. What I encourage you to do is put these equations in Desmos, and you can verify what the graphs can look like that way. It's a good way to check to see what you're doing is correct. Okay, for number 3, the parent function is the square function. I can tell because it's rounded. This is representative of a parabola. This is not the absolute value function. I notice that in general, all the points are relative to each other in the same way you'd see on the basic graph, x squared. But it looks like the graph has shifted to the right by 2 units. Because this is a horizontal shift, that means that h in this case is going to be equal to 2. But be careful because this goes on the inside and we're going to use subtraction to create the equation. So the parent function, I'm going to keep in mind, is x squared. But because this is horizontal, this is going to go on the inside of what the function is going to do. So instead of tacking this onto the outside like you would for a vertical shift, this has to go on the inside of the function. So this is going to become x minus 2 because that's what our original formula states. So this would become the equation of the graph that we're looking at. So this is a square function that was shifted to the right 2 units. H is equal to 2. And y is equal to x minus 2 quantity squared. The next function, this is a cube root. A cube root function. This has been shifted to the left by 4 units. What used to be at 0, 0 is now at negative 4, 0. I'm going to say this is h is equal to, in this case, negative 4. And we're going to create the equation. This is y is equal to the cube root of x minus, because that's what the formula tells us to do if we're on the inside, use subtraction. So this becomes x minus a negative 4. So ultimately our answer when we simplify it is really going to be the cube root of x plus 4. Okay, number 5 in this example, we're going to go from the equation to the graph. We're going to do that by identifying the parent function, HK, what shifts we can expect, and then we're going to go use a table of values to create the graph, but we're going to keep in mind what we learn about this function. So we have, on the inside of the function, we have x minus 2. So think about how that's going to change our graph, and then on the outside, we have plus 3. So we're going to know that h is equal to 2. We have k is equal to 3. So we can expect that this basic graph of the absolute value function so it's still going to look like that v, but it's going to shift up by 3 units. And x minus 2, we identify h to be 2, and this tells it's going to go to the right by 2 units. So the vertex used to be on the base on the parent function graph. The vertex was at 0, 0, and now that point is going to translate to 2, 3. So what used to be at 0, 0 is going to go to 2, 3. Okay, so we're visualizing that. Hopefully, if we do this correctly, we're going to visualize that V, and we're going to say there should be a vertex at 2, 3. And then another point that we can plot from 2, 3 is 1 up and 1 over. So we can plot another point if we're using the shape of the parent function, would be at 3, 4. We can also plot another point symmetric to that, would be at 1, 4. And then up and over 1 more, 1, 2, 3, 4, 5. 0, 5. And then we can also check this point here, which would be at the same height, 4, 5. So we're going to use the formula to check this relationship. We made a prediction based on identifying h and k, but it also has to work with the original equation. When we drop an input and output value, these ordered pairs should match up. So I'm going to check 0, 5. If I have y is equal to, and my x coordinate is 0, I get 0 minus 2 on the inside, and then plus 3. Let's check to see if we get back 5, which is the ordered pair anticipated. So this becomes 2 plus 3, which is equal to, hey, we got 5. That works, so that checks that point for us. You can try that with the other points on the graph. You want to keep in mind that the equation should validate the graph, and the graph should validate the relationship that's happening in the equation as well. So if I have y is equal to, if I want to check this point here, I'm going to drop in a 3 and see what we get. If we're correct, we're going to get back 4. Don't force it to happen though, right? This is supposed to be your check. So do one step at a time. Okay, and this does work out. You'll notice that this will work out for all of them. I'm going to connect those points to represent all of the other ordered pairs that would be on that graph. The domain of this would be all reals, and the range for this would be any real number such that the y values, you notice we have a lowest value of 3 there, so they all have to be greater than or equal to 3. Okay. Let's call that lesson done.